This video deals with the various operations on binary search tree. When the value to be inserted is k, we first perform a search operation on the binary search tree. If the search succeeds, the element already exists and we do not insert it again, to make sure that the keys are unique. If the search does not succeed, we insert it at the point it failed. That is, we put it in the place where it would have been looked for, next. To do so, we compare the new value with the value in the node where search failed and insert it on left or right depending on whether the value in the node is greater or smaller. Consider we are trying to insert 12 into the tree shown. We start from root and traverse till we reach 15 and see that the search fails as 15 has no left child. We insert 12 as the new left child of 15. It can be seen that performing another search for the element 12 would now succeed. Since we insert a node at the point it fails, and no other node is added as a child of the new node, it is always a leaf when inserted. The only extra step when compared to searching in binary search tree is the final step where the new node is added as a leaf. So the time complexity is the same as that of search, which is big O of height. Let us now consider removal of an element from a tree. We assume that the element being removed is present in the tree for obvious reasons. There are 3 cases to consider depending on the number of children that the node being deleted has. A leaf node can be deleted without affecting the property just like a new node was inserted as a leaf while retaining the properties of binary search tree. For example, the node 12 can be deleted by unlinking it from 15 and the new tree would still be a binary search tree. When a node has one child, the absence of the node in between does not affect the properties of binary search tree. So, we can remove the node by creating a link between its parent and the only child. For example, deletion of 15 by making 20 as the new right child of 10 ensures that it is a binary search tree. It can be seen that all nodes in the right subtree of 10 must have values between 10 and 25 in order to not violate the properties, and hence, changing 15 would not affect irrespective of what its child subtree had. If the child was on the left, it would have had values between 10 and 15, and if it was on right, it would have had values between 15 and 25, both of which obey the criteria that the values must be between 10 and 25. When the node has both left and right children, we need to find a way to merge the 2 subtrees without affecting the properties of binary search tree. To do so, we either find the largest element in left subtree or smallest element in the right subtree. The element thus found is either the previous or the next value closest to k. Now we swap the values in these nodes. The binary search tree thus formed does violate the property. We remove the node with value k to ensure that the properties are restored. The newly found node always has less than 2 children. Consider that we are deleting 10 from the tree. 10 has 2 children, 5 is the root of the subtree on the left and 15 is the root of the subtree on the right. 10 can be deleted in 2 ways. First, we find the largest in left subtree, which is 5 and swap the value with 10. Now 10 is a leaf and is deleted. If we consider the right subtree, the smallest value in the right subtree of 10 is 12. We swap the contents and 10 is now a leaf and can be deleted. We have claimed that the new node always has less than 2 children. Consider the case where m is the largest element of the left subtree. Then m will not have a right child because if it did, then that would be greater than m, which contradicts the assumption that m is the largest. Similarly, the smallest element in right subtree will not have a left child. In either case, the node will have less than 2 children. It takes big O of the level of n time to reach n. If n has 2 children, it takes some more time to find m. In all the cases, we are only going down the tree and in the worst case, we can go till the farthest leaf. So the worst case time complexity is big O of the height of the tree. We have seen that binary search tree allows you to search, insert, and delete elements in big O of height. We can also create a binary search tree by inserting all elements one by one. This takes time equal to the sum of heights at each insertion. It might be good to find out the minimum and maximum time that is taken for the same. Big O of height operations might seem attractive, but how does height vary with the number of nodes in the tree? Is it always small? What is the maximum value it can go to? Answers to all these questions will be provided in the next video that compares binary search trees with arrays and also discusses some ways to optimize binary search trees for specific applications. If you have any questions, post it in the comments below or post them on the website. For more resources, do visit the website. The link is provided in the description below. Happy coding!